Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's biweekly contest. Find the sum of subsequence powers. The problem is actually a hard problem, but as always, I will start from scratch, try to build the intuition step by step and get to the final solution. We will be discussing two different solutions, one which is of the complexity n power 5, second which is of the complexity n power 4. So if you are here just for one particular section, all the timestamps will be there in the description down below. You can watch the section which you like, but having said that, would strongly encourage you to watch the entire video for a better understanding. To ensure that the video doesn't go above a certain length, I might skip the dry run of few small part of the solution and will leave that to an exercise. Having said that, if you face any issues understanding those things after rewatching the video, feel free to post that in the comment section below and I will try to answer it in as much detail as possible. So let's get started. The problem states that you are given an array nums and a positive integer k. The power of a subsequence is defined as the minimum absolute difference between any two elements in the subsequence. We have to return the sum of power of all subsequences of nums which have length equals to k. So let's take an example. Let's say nums is 1, 2, 3, 4, k is 3. So we have to figure out the sum of power of all subsequences of nums of length 3. So how many subsequences of length 3 are there? 4c3, which is 4, and what are they? 1, 2, 3, 1, 3, 4, 1, 2, 4, 2, 3, 4. And if you figure out the power of each of them, the power of this one would be 1, because power is defined as the minimum absolute difference between any two elements. So minimum absolute difference. You can see 1 minus 3 is 2, but 2 minus 3 is 1. So minimum absolute difference is 1. So the power of this subsequence would be 1. Similarly, power of this subsequence would be 1, because 3 minus 4 is 1, and that's the minimum absolute difference. Similarly, the power of this subsequence would be 1, 1 minus 2, and power of this subsequence will also be 1. So there are 4 subsequences, each has power 1. If you sum them all up, you will get 4, and hence 4 is the answer. So hope the problem statement is clear. Now, what is the brute force solution? For a moment, let's forget about k. Let's say you have to figure out the sum of power of all the subsequences of the given array. So the brute force solution could be, you will figure out all subsequence, figure out their power and sum it up, right? So there are total 2 power n subsequence. You will enumerate all subsequence. Let's say the first one has power p1, second one has power p2, third subsequence is power p3, and so on and so forth up to p2 power n, right? And you will just sum them all up and that will be your power. So what will be the time complexity? You will enumerate all 2 power n subsequences, and for each of them you will calculate the power. So cost of power, that we are not calculating for now because 2 power n itself is very huge, right? You might argue that, okay, if we have taken k, then this would not be 2 power n and it might have been better. But if you think about it, it would be nck only, and nck is also equally bad. You can't pass it. You can't fit this in the time complexity as well, because n is 50, so n factorial would be very huge. So both of them are equally bad. So it's okay to solve it for without k, and then we'll introduce k later, right? So we saw that this brute force solution will not work, right? We have to somehow optimize this. Now, what is the intuitive or most intuitive way to optimize this particular piece? You want power, sum of powers, right, at the end. So you want p1 plus p2 plus p3 all the way up to p2 power n. So instead of enumerating everything, you might say, okay, how many times p1 occurs among these 2 power n subsequences? Let's say x1 time. How many times p2 occurs among this 2 power n subsequences? Let's say x2 times, and so on and so forth. So you can now sum this thing up and you will get the exact same answer, right? So what is the benefit here? The benefit is now you have clubbed the subsequences which have equal powers together, right? Now, will this help? The answer depends on the fact that how many different powers can be there, right? Number of distinct power will be equals to number of expressions here, right? So how many distinct powers of a particular array can be there? Power is defined as minimum absolute difference between any two element in the subsequence. So in worst case, power will be the difference between every two element, right? So in worst case, there are total n square number of distinct differences, and hence in worst case there can be at max n square number of such expressions. So notice you can't iterate over each of these because there are 2 power n of them, but there are just n square of distinct powers, so you can iterate over each of this, right? So you can turn your approach and say that, okay, instead of finding out every subsequences and then power of every subsequences, I will figure out for how many subsequences are there which has a power of some, let's say d, right? Now what does d means? D will denote the minimum absolute difference between any two element in that subsequence, right? So our task is to find out how many subsequences are there which has a power of d, and I will do this for every possible power and sum them all up to get the answer. So the new problem statement is number of subsequences. We have to figure out the number of subsequences with difference between every element greater than equals to d. Now why greater than equals to d? Because for d to be the power, the minimum absolute difference should be equals to d, right? So every other differences should be greater than equals to d, right? So that's our new problem. If you were not able to dissect or reach this state of the problem before, this is the very right time to pause the video and give this problem one more try. So notice we need to figure out number of subsequence between every element where difference between every element is greater than equals to d. Assume that d is 2 for this example, right? So let's say you have a subsequence. Let's say you have subsequence 5, 6, 2, right? Let's say you get this subsequence. Now is this subsequence a valid subsequence or not with respect to this definition of d? To answer this fact, you have to actually figure out the differences between every two element, and if none of them has a difference of less than 2, then this is a valid subsequence, otherwise this is not a valid subsequence, right? So to even answer whether a subsequence is good or bad, you need all the element of the subsequence right now, and until you need all the element of subsequence right now, you can't afford not iterating over subsequence. To repeat, we want to figure out the number of subsequences where difference between every element is greater than equals to d. Now we get to this state just because we don't want to iterate over every subsequence, right? Now what we are saying is, to even understand whether a subsequence is good or bad, we need to enumerate all its elements, and if we need to enumerate all its elements, we have to enumerate all subsequences at the end. So what we were trying to avoid, we have to do it now, so there is no advantage here. So if we actually want to gain the advantage here, we somehow need to able to figure out whether the subsequence is good or not without actually having all the element at once. Until we do that, we can't actually optimize this solution at all, right? So the task is, without having all the elements, can you say whether the subsequence is good or not? So the answer is yes. Let's just sort the element. Let's say 2, 5, 6. Now to actually figure out whether the subsequence is good or not, you don't need to now find the differences between every element here. You can simply find the differences between adjacent element and if they are satisfied for the given criteria D, every pair will be satisfied, right? Because minimum difference will be between adjacent elements, right? And because the minimum difference is between adjacent element, if you can somehow figure out the, or if somehow you can figure out what is the difference between the adjacent elements, then you don't need to have every element with you, right? So let's just sort the array first. So let's say we have sorted this array and this is the new array. So we'll work with this array for now. Now in this array, you have to figure out the number of subsequence with diff between every element greater than or equals to D. So let's say you look at the first element. So first element, you will either take it or you will not take it, right? So if you take it, what is the second element you can take? You want the difference between them to be greater than or equals to D. So can you take 2? The answer is no. If you have taken this, you have to take 3 now, or at least anything greater than 3, right? Now once you, let's say you decided to take 3. Now once you have taken 3, you can simply ignore the fact or forget the fact that you have taken 1 as well. You can now work with 3 only. You can say, okay, now I know that I have 3 with me. So what is the next element I can afford? I can't afford 4. The next element should be at least 5. So the next element can be greater than or equals to 5, right? So notice, now you don't need every element here. You just need what is the last element I have taken, right? And with this shift, you can simply memorize this solution and work with a simple recursion, right? So let's just figure out the recursion here, and then we will go back to the original version of the array and see why that was not working for one final time. So here at every index you have 2 choices. Either you will take it or you will not take it. So if you don't take it, then what is the problem? The problem is, find the number of subsequences in this remaining array such that the difference between every 2 element is greater than or equals to D. Okay, this is exact same problem as the original problem, except the original problem was on bigger array. This problem is on a sorted array, sorted array. Now let's say you have taken this first element. So in this case, what you will say, give me what is the number of subsequences possible such that difference between every 2 element is greater than equals to 2, given I have the last element I have taken is 1. So that in turn means whatever element next I will take should be greater than equals to 1 plus 2, which is 3, right? So this is also exactly equals to the original problem, just with the reduced constraint, and the last element has now changed, right? Previously you were able to take this because there is no element at all, so you can assume that there was minus infinity, right? But once you have taken this, you have said that the last element I have taken is 1 and this is my remaining array. Now tell me what is the number of subsequences that is possible that satisfy this D, right? So hope you can see the recursion here. Let's just try to formalize the recursion before we actually do a dry run. So let's say f of array with the last element that you have taken, right, is giving you what is the maximum number of subsequences possible with this array, given this is the last element you have taken, right? Now here you have 2 choices. Either you will take the first element or you will not take the first element. I am talking about the first element of this array, right? So if you don't take the first element here, you will you will remain with a shorter array, right, where this element was not there, right, this element is not there, this is shorter array, and the last element is still the same. Whatever was the last element is still the last element. You haven't taken anything extra now. Now if you have taken this, you will say give me the number of sequences possible with this remaining array. Again, this remaining array doesn't have the first element, and the last element this time is array of or array of 0, where array of 0 is the first element of this particular array, right? So once you figure out, like, again, for this you will do the exact same thing, right? You will either take the first element or you will not take the first element, and for this you will again do the same thing. So that's the recursion part, right? So hope this particular piece is clear. Now just to formalize this a bit, instead of taking this entire array, we can work with a simple index here. Why? Because we know that we are only dealing with the first element. So whatever remaining array is there will be a suffix of the original array itself, right? So after working with the first element, this will be my remaining array, right? Now when this is the remaining array, I will work with the first element again, and after I am working with the first element, this is now remaining array. So every time the remaining array is just a suffix of the original array. So instead of copying the entire array with you, you can simply maintain an index which will say starting from which index is the array I am currently considering. So f of I will means starting from ith index, whatever is the array remaining is my array which I care about right now, right? So if you do this, this will become I plus 1. This will also become I plus 1 because you have decided what to do with the ith element, right? And this will become a of I. Basically you have taken you have taken a of I as your last element, right? So this is the overall recursion. Now just to reiterate the initial part of that we have discussed, so we can't do the exact same thing with this array. Why? Because if you have, like, let's say you do the same thing, you say this is the ith element, I will either take it or I will not take it. So if you, let's say, take it, so you have this 5. Now once you have this 5, next time you will say, okay, I will not take anything between 3, like I can take anything less than 3, or I can take anything which is greater than equals to 7, right? Now let's say you pick 3 here, right? Because you can take 3, so next you pick 3 here. So once you have taken 3, you will forget about 5, right? Now if you forget about 5, there is an issue. Why? Because whenever 5 was there, you can't have taken anything between 5 and 7. But now, because you have forgotten about 5, 6 is now a valid candidate, right? But this is not a valid candidate if 5 was also there, right? So because there was no ordering before, you have to have all the elements with you, so that after all the elements you will sort it and get the order and then figure out whether it satisfies the given constraint or not, right? So that's where you actually have to sort the entire array first to make sure that you will only depend on the last element rather than on the entire array, so that you don't need to maintain the entire array with you, and that's how you will save on the complexity, right? So I would, if it is not clear, just rewind the section and watch it again. I'm very sure you'll be able to get it. So overall what we are saying is, to figure out the number of sequences with diff between every element greater than equals to d, we'll first sort the array. After we have sorted the array, we can simply depend on the last element of the array, a last taken element, and build a recursion out of it. Now once you have built the recursion, you can simply memorize it to make it efficient. So if you look at the pseudocode would be exactly similar to what we have just written here. We will have index, which will denote after what element you have taken is the array you are considering, and you have last taken, which is the last index or the last element, whatever you call it, is that you have already taken. Now if you have decided what to do with every element of the array, that is you reached the last element of the array, you will simply return 1. That is, you have decided what to do with all the elements, so you have actually formed a valid subsequence. Now otherwise you will decide what to do with the current element. Either you will not take it or you will take it. So if you don't take it, it will simply be f of index plus 1 comma last taken, and if you take it, then notice that you can only take it if the difference between the last element you have taken and the current element is greater than or equals to d. And if that's the case, you can actually take the current index as well, and in that case you will say that give me the total number of subsequences possible where the first element where the last element that I've taken is at the index ind, right? So if this part is not clear, just stick around it. We'll do a dry run in a while to make this very clear, right? So overall we are saying that with this recursion, in just order n square time, we will be able to figure out what is the number of sequences with the diff between every element greater than or equals to d. Now why order n square? Because we will do memorization, so every state we will calculate exactly once. Now what we are doing inside each of the state, we are simply calling few function and doing some mathematical operation. So this is order 1 operation, right? And how many states can be there? Distinct value of index multiplied by distinct value of last taken. Again, last taken can be a value or can be an index. In this case we have taken it as an index, so the number of distinct value is also n. So overall total n square different state, and inside of this state you are doing order 1 operation, so overall complexity is order n square. So in order n square you are able to figure out number of sequences with the diff between every element greater than or equals to d, right? Now notice we had a k as well, right? So we need to figure out number of subsequences with length k and difference between every element is greater than or equals to d, right? So let's now take k into consideration. Now again, if you understand the previous part, this part should be very easy for you. You should be able to do it by yourself. Notice we have already sorted the element because we still want to figure out the scenarios where difference between every element is greater than or equals to d efficiently. So sorting the element is required. Now once you have sorted the element, again you will do the exact same thing, figure out what to do with the first element. Either you will take it or you will not take it. If you don't take it, the remaining array or the remaining problem is, in this remaining array find me the number of sequences of length k such that the last element I have taken is still minus infinity, right? And let's say you have taken it. In this case you will say, in this remaining array tell me the number of sequences possible with length k minus 1, because you have taken one element already, such that the last element you have taken is 1, right? So both of them are exactly the same problem as the original problem, so you can do recursion here as well. So let's just write the recursive formula one last time. So we have f of some array where we want to take only k elements, and we know that we need to satisfy this condition, and to satisfy this condition we need to have the access to the last element as well. So let's take that into account as well. So this is our function which will return the number of sequences with length k and difference between every element is less than equals to greater than equals to d. So here you will do two things. Again, you will only care about the first element of this array, right? So either you will take it or you will not take it. So if you take it, the number of element in the new array reduced by 1, so this element will not be there in this new array, and you will have take only k minus 1 extra elements because you have taken one element already, right? And the last element you have taken is array of I, or the first element of this array, right? And if you have not taken it, then you will again be remaining with the some remaining array where this element will not be there. This time you have to take k more elements because you haven't taken any element at all, and the last element you have taken is still whatever the last element you had previously, right? So again, you can remove this array with an index, because this array will always be a suffix of the original array, because what you're doing is deciding what to do with the first element of the array. So every time you decide what to do with the first element, you will be the remaining array would be a suffix of the original array. So you can simply replace it with an index, and this index will denote, if this is I, this will denote this is the remaining array. Everything starting from I up till the end is the remaining array I am considering. So this will become array I plus 1, and this will also become I plus 1. So this is the overall recursion. Again, this is not very different. Only difference is we have included the variable k as well, because that will denote the number of elements that you have to take. Now with this, one more thing will be there. The base case will also change. Why? Because now when you reach to the end, you have to now check whether you have, so if you reach till the end, you are sure that this condition is satisfied, because you will only take elements if they match with this condition, right? So along with this, you now also have to make sure that you have taken all the k elements that you require. So at the end, you also have to check whether the k remaining is 0 or not, right? So that's the only difference. So the pseudocode for that would look something like this. Again, if you face difficulty in converting this recursive formula into a function, don't worry, we're doing a dry run in a moment, which will make this a bit more clear. So we have this index last taken and k. Again, this two were the exact same thing that we had previously. We just added a k as well, which denotes the number of elements we have to take, right? Now the base case will change slightly, as we discussed. This will have one more criteria, which is if k is 0, then only we have find a one valid subarray subsequence. If k is not 0, it means even though we have taken some elements, we are not able to take all the k elements required, and hence whatever subsequence we have made so far is not a valid subsequence. Let's assume that you have decided to take 2, 4 and 6. So whatever you have decided to take is not equals to what the value of k is, and hence the subsequence that you have made so far is not a valid subsequence. So after this base case there, you will just for a particular index, you will see if either you will take that index or will not take this index. If you don't take this index, last taken will remain as it is. Number of elements you have to take more will remain as it is. But if you take the index, number of elements you have to take more will decrease by 1, and the last taken index will also reset to IND, right? So overall, the complexity of this function is now order n cube instead of order n square, because again, the only thing that change is you are doing order 1 operation inside this function for each state. Number of states is now not order n square, instead order n cube, because k can also be up to order n. So in order n cube, you are able to figure out number of sequences of length k where the difference between every element is greater than or equals to d. So if you have understood this point, the next section you can skip freely and move to the section after that. The next section we will be just doing a dry run of this entire thing for those who still face some issue in translating that recursive formula into a recursive function. So assume this is the array, right? And we need to figure out number of sequences of length k. K in this case is 2, right? And difference between every element should be greater than equals to 2 as well, right? So this is what we need to find out. So what we need to find out, f of 0. Why 0? Because we need to take care of the entire array. So 0 means everything after 0, which is the entire array, comma last taken. So last taken was the index. If you remember, we have not taken the value. So if we have taken the value, it will be minus infinity, but we have taken the index to ensure that the complexity stays within the bound. So assume that there's a invalid index which is -1 somewhere there that you have taken, and the number of elements you need to take is k, which is 2 in this case, right? So this is what we need to find out. So that is what we are trying to find out as well, right? Now from here you have two choices. Either, okay, first of all, you will decide what to do with the first element of the array. So this is your array, right? Because you have said that you will consider the array that will start from 0. So this is your array. You will decide what to do with the first element. First element is the 1. So you will decide either you will take it or you will not take it. So if you don't take it, then you will be remaining with this array, right? And you need to figure out the number of sequences of length 2, because you have not taken any element at all. So still you have to take you have to consider length 2 for this remaining array. So remaining array starts at 1, so the first value is 1, and the last element that you have taken is -1 because you have not taken anything yet, so it's still a dummy value which is -1, right? Now this is the first criteria where you said that you will not take it. Now let's say you take it. In that case, number of elements you need to take more will be decreased by 1. The remaining array will also be starting from index 1 itself, and the last element that you have taken, or the last index you have taken, is 0, right? So that's where we have said marked as 0, that is the 0 is the last index you have taken, right? So let's expand f of 1 comma -1 comma 2 this time. So notice the first element is 1, that means you are taking into account the array which starts at index 1. So this is the array you are considering. This is -1, so the last element you have taken is -infinity. So there is no burden on whether you can take this element or not. You can take this element, right? Because the last element was -infinity, so this element is a valid first element, and you have to take 2 elements with you, right? So again, two choices: you will not take it or you will take it. If you don't take it, you will be remaining with this array which is starting at 2. Again, previous element will still be -infinity because you have not taken anything, and number of element you have to take more is 2, right? And in case you take it, then number of elements you have to take more will be decreased by 1, and because you have taken this element, this is your last element now, because that's the last element you have taken. So index is 1, right? And next array, or the remaining array, will be the one that starts at index 2, so that will come 2, right? So let's expand this one for one final time. F of 2 comma 1 comma 1, that means this is the array you are considering, right? Starting at 2. This is 1, which means the last element you have taken is this, right? And this is 1, which means you have to take one more element, right? Now here, two choices: either you will take it or you will not take it. So if you don't take it, it is simple, you will be remaining with this array. You have to take one more element, right? And the last element you have taken is still the 1, right? So this is f of 3 comma 1 comma 1, right? But here the other choice is not there at all. You can't take this index. Why? Because if you take this index, difference between these two will become 1, and you want difference between adjacent element to be greater than or equals to 2 always. So that's where you can't take this index at all, and that's the only choice. F of 3 comma 1 comma 1 is the only choice here, right? Now you will move forward. Let's do one last time. F of 3 comma 1 comma 1, which means starting from here, what is the number of sequences possible such that the last element I have taken is at index 1, which is 2, and we have to take one more element. So here again, index 3 we have to decide what to do, whether we will take it or we will not take it. If we not take it, then the remaining array will start at index 4, right? And the number of element remaining would be 1, and we have to take the last element that we have taken will still be the 1, right? But if we take it, if we take this, first of all we need to decide whether we can take it or not. So that we will check. The current value is 4, the value of the last element we have taken is 2, so 4 minus 2 is 2. So number of the difference between the adjacent element is 2, so that is greater than or equals to 2, so we can take this element. So if we take this element, the next is this array which is starting at index 4. So starting at index 4, given that you have taken the last element at index 3 and you have to take 0 more element, so for this you will always return 1 in this case, and once you return 1 here, you will return something else from here. Let's say you will expand something here, you will get something, and you will sum them all up, that will be the value here, you will return that here, and so on and so forth, and finally you will get the value of f of 0, minus 1, 2, right? So hope this entire thing is clear. So now if you go back and look at this recursive function, that might make more sense. We have f of index last taken and k, and if index is n, we will check whether we have taken all the elements or not, and if index is not n, we will decide what to do with the current element, whether we will take it or we will not take it. So if we don't take it, this will be the state. If we take it, this will be the state. And notice we can take it only when this condition is already satisfied, right? So hope this thing is clear. Notice we have to memorize this as well. I haven't shown the code for memorization, but you have to memorize this entire thing, because the same state is something you might end up calculating again and again, right? So now what we have two things. First, we know that we wanted to figure out d1 multiply, like this was your expression, right? This is what you wanted to figure out, d3 x3 and so on and so forth, right? And you will sum them all up to get the answer, where d1 is the difference between d1 is the possible difference, d2 is another possible difference, and so on and so forth, and x1 is number of subsequence with this power, number of subsequence with this power, number of subsequence with this power, right? So that's what your final answer was. Now to figure out x1, you have this function, right? You can simply say for a single d how to figure out number of subsequences of length k such that difference between every element is greater than or equals to t, right? And now you can say that, okay, I will simply figure out the diffs between all the unique diffs between the array. How to do that? Just do a n square loop and figure out the diffs between every element of this array. So 1 minus 2, 1 minus 3, 1 minus 4, 1 minus 5, 1 minus 7, 2 minus 2, 2 minus 4, 2 minus 5, 2 minus 7, and so on and so forth. So you will see the number of unique diffs you will have will be in worst case of the order n square, right? So there are total order n square diffs here. For each of the diff, you will reset this entire matrix of whatever you have memorized, you will reset that and calculate the value of f of 0, minus 1, k, right? And once you have figured out that, you will simply multiply it with the diff to get the value of one expression from this, and you will do this for all the diffs and you will get the final answer, right? Now it's all correct, and the complexity will be of order n power 5, because if you remember, this was of order n cube and you're doing this for all the diffs, which is n square. So order n power 5 is the complexity, which will pass because of the bad because of the poor test case, I would say. But there is still a gap here. The gap can be figured out if you run this part for d equals to 2 itself, right? So I would encourage you to pause and try to figure out the gap by yourself. So the gap is, notice for d equals to 2 what you will get from this function. You will get the number of subsequences of length k such that difference between every element is greater than or equals to d. And what is power? Power is minimum absolute difference between any two element in the subsequences, right? So for D to be the power, you have to have two at least once, otherwise D can't be power. You can say that okay, there is a subsequence where every element is greater than or equals to D, but no element difference between no two adjacent element has a difference of D. Everything is greater than D. So in that case, this D can't be power. So whatever your assumption was here, that these many times D will be the power, will be wrong, right? So just to take an example, in this case, if we have taken 1, 4 and 7, this is a valid subsequence for D equals to 2, right? Because by definition, you will select, you can select 4 after selecting 1, because this 4 will satisfy this particular constraint, right? Similarly, after selecting 4, you can select 7. You might skip 5 completely, right? So this is a valid subsequence for this, for D equals to 2, but this subsequence doesn't have a value of 2 or doesn't have a power of 2, right? So that's the gap. Now, how to fix the gap? It's very easy. Think of this greater than equals to and pause the video and try to fix the gap by yourself. So hope you thought about it. The answer is very straightforward. Notice you are figuring out the number of subsequences where the value of the diff is greater than equals to D, right? Now let's say you figure out the value of subsequences where the value of diffs is greater than equals to D plus 1. So will this two has a relation? The answer is yes. This will be a superset of this one, right? Why? Because number of subsequence, okay, I think I have yeah, number of subsequences with only 2 will be like this. Number of subsequences with only 3, let's say, is this part. Number of subsequences with D has 4 is this part, and D has 5 and other part. So when you calculate the number of subsequences where D is greater than equals to 2, you will get this entire circle, right? And when you calculate the number of subsequences where D is greater than equals to 3, you will get everything but this, right? So apart from this, you will get everything. You can just subtract these two and you will get number of subsequences where the diff is where the power is exactly 2, that is one of them is exactly equals to 2. So you can modify the previous algorithm slightly to just maintain the previous count as well, and whenever you figure out the count for a diff, notice this time you have to iterate over the diff in the reverse order. So let's say the number of diffs are 1, 2, 3, 4, 5. Assume that this is the diff. So instead of iterating from 1, you will now iterate from 6, right? Because 6 is the one which you can figure out independently, because you know none of the diffs are greater than 6. So whenever you will consider subsequence where the diff is greater than equals to 6, that subsequence must have 6, right? No other choice is there. So you will first figure out this count for 6, and then you will figure out the count for 5. Whatever count you will get, let's say you get x and you get y here. So when you figure out the contribution of 5 only, you will do x minus 5, right? And let's say you get z for 4, so you will do z minus x. So you will simply subtract the previous one and you will get the answer, right? So hope this entire thing makes sense. So overall complexity is order n power 5 if you look naively, and that will pass the given time constraint, right? Now you can implement this by yourself. The pseudocode will look exactly like this. This part we have discussed how to modify this. Now you can optimize this easily to order n power 4 as well. How? You can remove, notice like you can't remove this order n square first of all. So only thing you can do is you have to remove this order n cube from this function. And removing order n cube means that you have to remove one of these variables, because that's where 3 n's were coming from. So k you can't remove because you have to consider that you have to take k elements. Index also you can't remove because that will denote what is the remaining array you have to take into account. So only thing you can remove is last taken, right? Now what does last taken was doing here, and if you can somehow replace it with some pre-computation, you can get rid of last taken completely. So would encourage you to pause again and try to think by yourself at least for 5-10 minutes. So notice what last taken was doing. Last taken was simply taking care of the fact that whatever next element we take should be greater than equals to d. The difference between that and the current element should be greater than equals to d, right? And how we can avoid this? This condition was coming because whenever we are jumping to the next index always. Now instead of jumping to the next index, if we somehow know that, okay, if we have taken the current index, then what is the valid next index I can take, and if I jump directly to there, we don't need to maintain last index, right? Just to reiterate, last index is required because we are using it to determine whether to skip the current index or not based on what we have taken previously. Now this, if we somehow directly jump, like we know that, let's say let's take concrete example, let's say index is this, right? And last index is this, right? Now when you're here, you have to somehow know that what you have taken previously, and based on that whether it is valid value or not, right? So again, assume that d is 2. So in this case, this I is not a valid I, because you can't take this I because this L is something you have taken already, right? So to skip or to avoid taking this I, you have maintained this last index. Now instead of this, what if whenever you have taken any index, you will forward the I to the index which is a valid index, or rather after which all the indexes are valid. So if you do this, then you don't need to maintain this L, because you know that whatever I will land at will be a valid index to take, right? So that's what is something you need to calculate. So for every index, if you can calculate that what is the next index which from which I can start taking the values, if I have that array with me, then I can, instead of doing this and this, I will just simply do, let's say the array is next, so next of index is something I will directly jump to, and in that case I don't need to maintain the last index as well, because I know next of index will be the one which I can take if I have taken the current index, right? So that's the entire game. So instead of taking the last index here, you will simply maintain a next array. So let's take an example. Let's say in this case, next array would look something like this. It's a d is 2, right? So, and this, let's just reword this as well. So next array for 0 would be 2, because if you have taken 0, you can take anything starting at 2. Similarly, next array of 1 would be 3. Next array of 3 would be 4. 2 would be 4. Next array of 3 would be 5, right? Next array of 4 would be 5 as well, and next array of 5 would be 6. Let's say 6 is nothing. So once you have this, whenever you take any index, you just forward your I to that index. So if you have taken this 0, you will forward your I to 2. You will not take your I to 1. Right? That's the only change you have to do, and in that case you don't need to maintain the last index. And because you don't need to maintain the last index, you can simply, this entire thing will simply be order n square, right? And you will do this n square time for the n square diffs you have. So overall you will be doing order n power 4 operations. Now notice you have to calculate this next array for every d. So for every d, you now have to calculate the next array for every I, and for that you can use two pointer. I have not used two pointer here. So if you do it naively, that will also take order n square. So overall you have order n square here as well, which overall is order n power 4 only. But you can simply optimize this to order n as well using two pointer because of strictly increasing. If you don't understand why you can optimize this, I think the third problem of today's contest was exactly on these lines, and I have a video already on that. So try to watch the last section of the video and you will understand why, how to optimize this from order n cube to order n square to order n, right? So overall the complexity is now order n power 4. So if you have watched this point, strongly encourage you to pause and try to code this entire thing by yourself before moving forward in the video. Next we're looking at the code. The code is exactly what we discussed. We will first sort the array and then we'll figure out all possible differences. So how to figure out differences? Just iterate over all the n square pairs and insert them into a set, right? So this set will contain unique elements only, and now I will just created a vector out of this set, right? Just to make sure that I don't end up paying order log n operation per axis, right? After that we will iterate over each of the differences, and for each differences I have calculated the next array, or I built the next array. This is something I have built using the naive fashion, but you can use two pointers here as well, right? Now for this I, we want the next j. So basically the first j where this condition is satisfied, that's the j I am looking for. So I will figure out that and I will break. And after that we will iterate over each of these differences again. For each differences we will count the number of subsequences for that differences. Notice I have taken diff as well into account in this recursion, but you can simply move this statement inside the loop and get rid of this diff as well. So that's just like we are simply not resetting it every time. That's why we have maintained the different dimension altogether, but this can be avoided very easily. Inside that, the logic is exactly what we have discussed. We will simply take in, will not take the current index, or if we take the current index, we will directly jump to the next valid index, right? And once we figure out the number of sequences for greater than equals to d, we already know the subsequences which is greater than equals to d plus x, whatever was the differences there. So we will subtract those two and multiply with the diff. That will be the power, so number of subsequences with this particular power, and you will add this to your result and you will keep on doing this for all the differences and you will get the answer, right? So hope this entire thing is clear. I know this was a bit involved, so all the timestamps will be there in the description down below. I would encourage you to go through the entire exercise by yourself once and see which part doesn't seem very intuitive to you and rewatch that particular section. As always, comment sections are always open, so if you have any doubts, feel free to post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. I will see you in the next one. Thank you.